Assalamualaikum. Myself AKLIMA. Today I am going to talk about our project topic 3-bit up/down synchronous counter. Here are our group members who will discuss about the project. These are the context where we will discuss about abstract methodology, calculation, apparatus, simulation and conclusion. In abstract, we will learn about flip-flop and counters. We will learn about principle and working mechanism of counter. Synchronous and asynchronous counter. We will learn about regular and irregular counter. We will learn about up/down counter, and we will design and simulate up/down counter. So let's talk about flip-flop. Flip-flop is a synchronous bistable devices that have two stable state. It is basically used to store binary data. It is known as basic storage element in sequential logic. Clock mechanism in flip-flop makes the difference from latch. So here are the block diagrams of D flip-flop and JK flip-flop. D flip-flop have only one input D, and JK flip-flop have two input J and K. So in our project, we are going to use JK flip-flop. So let's talk about JK flip-flop. JK flip-flop have two inputs J and K. It is an alternation of the SR flip-flop. Here are the IC diagram of JK flip-flop and the symbol of JK flip-flop. In clock, J equals 0 and K equals 0, the state remains same. When J equals 0 and K equals 1, the state become reset. When J equals 1 and K equals 0, the state become 1 or set. When J and K both are 1, the state become toggle. So that's all from my side. Our next presenter will continue the next part.
Assalamualaikum, I am AKTHER. I'm going to talk about the counter. So what is counter? A counter is a device which stores and displays number of a particular sequence. It is mainly used for counting purposes. A counter is a sequential circuit which is made by using flip-flops. If we want to make n-bit counter, we have to use n numbers of flip-flops. There are two types of counter. Let's talk about the asynchronous counter using JK flip-flops. In asynchronous counter, the flip-flops receive different clock signals. Here, all the inputs are high, and the output of the system clock is applied only to the first flip-flop, and the remaining flip-flop receive the clock signal from output of its previous stage flip-flops. A asynchronous counter only can count up count. Here is a block diagram of a 4-bit up counter of asynchronous counter. Synchronous counter. In synchronous counter, the flip-flops receive same clock signals. Here input is the previous output. In synchronous counter, it can count any sequence of number and produce output at the same time.
Assalamualaikum, myself Jalal. Now I am going to discuss about sequential and non-sequential count. Sequential count that going one state to another state by sequentially, like 1, 2, 3, 4, like that. It maintain an order. And non-sequential doesn't maintain any kind of order. It going by randomly, like 0, 1, 3, 4, 5, 7. Now let's talk about up-down counter. Up-down counter can count ascendingly or descendingly, like 1, 2, 3, 2, 1. We in our up-down counter we use synchronous counter because it can count any sequence, like ascendingly or descendingly. We cannot use asynchronous counter because it cannot work as a down counter. It only work as a up counter. So we we cannot use asynchronous counter. We use K-map technique to design the counter. So next, calculation, non-sequential counter basics. Present state and next state when is 0 0, the J will 0 and K will be don't care. When present state 0 and next state 1, J will be 1 and K will be don't care. When present state 1 and next state 0, J is don't care and K is 1. When present state 1 and next state 1, J is don't care and K is 0. That's all my part today. Our next presenter will discuss about his part.
Assalamualaikum. My name is MAHMUDUR. So let's describe about transition table of JK flip-flop. So let's understand what happens in transition table of JK flip-flop. So here we first see clock, here J, K, and here is next state. So let's understand here is next is N plus 1. Okay, now we know already that when clock is 0, there is no output. So what we give at J and K, state remain same. So there is Q N, state remains same. Now if we give clock 1, now what will happen? Now if we put J0 and K1, our next state will be 0. If we put 1 and 0, our next state will be 1. If J and K both are high, our next state will go to toggle mode. Let's say toggle Q1, but what we have in memory, it will toggle. Okay, this is our transition table. Now let's see about what is characteristic table of JK flip-flop. So here is QN, here J, now K, and what is our next state is QN, plus 1. This is our next state. Now let's put our value 0 0 0 0 0 1 0 1 0 1 1 0 no 1 0 0. Let's try to understand from this value. Okay, let's fill up the truth table, characteristic table. Q1 is 1 1 1. Okay, so here when J0 K0, we already know that our in excitation table we already, okay, we didn't fill up this. 1 0 0 here Q1, so next state remains same Q1. So when J is 0, K is 0, this will be zero, because it's remains same. That's why Q1 is 0. That's why Q1 plus will remain same. Now when we put 0 and 1, what will happen? From excitation table it will go to reset, so it's 0. From 1 0 it will 1, from 1 1 it will go to toggle mode. But what is toggle? Let's see. Here is qn is 0, so our qn plus 1 will be 1. So here let's say j is 0, k is 0. We already know what will happen. Qn plus 1 will remain same, that's why it's 1. Now when qn is 1 and j and k both are 1, what will happen? It will go to toggle mode. Now it will be 0. Why? Because we already know that qn is 1. Okay, this is our characteristic table. Okay, now let's see what is excitation table. So from excitation table we already see from previous slide. Let's open our slide. So from previous slide we already know this excitation table. From this table we already know when present state is 0, next state will be 0. When j is 0 and k is don't care. Why this happened? Let's see from this characteristic table. So here j is 0 and here is 0, output is 0. Okay, from 0 to 0. So from 0 to 0 we see that this is our 0 0 and this is qn plus is 0 0. So when j is 0, both in j is 0 and k can be 0 and also can be 1, so k is don't care. So k, but we need j is 0. So when present state is 0, next state is 0, our j should be at 0 and k don't care. So similarly we know that when present state is 0 and next state is 1, let's see what happened. J is 1, k is don't care. From characteristic table, from 0 to 1, why it is 0 to 1? Here 0 to 1, here 0 to 1. Now j is here is 1, but k is don't care. That's why we can say that when we go to present state 0 to next state 1, our j will remain 1 and k is don't care. That's how we filled our excitation table. So this is our JK flip-flop, this is our JK flip-flop transition table. We can say also that this is excitation table. Okay, now from this state change transition table we know that we need 3 bit. So here is QC, QB, QA. This is MSB to LSB. Now this is our present state, this our next step. So let's take 2 examples from here, and we also know that what is control input M. So from control this M input, when we put 1, it will goes to 0 to up. When we put M into 0, it will goes down, that means 7 to 0. So let's do 2 examples from here. So let's see from first row what is happening. This is our LSB QA. So from 0 to 1, we want to go 0 to 1. What will happen? Here is JA is 1 and K is don't care, because we already know from our table that when present state is 0, next state is 1, J should be in 1 and K can be 0 or 1 both. We already verify it from our characteristic table. Okay, so here let's see. So from 0 to 1, JA is 1 and K is don't care. And QB, for QB here 0 and next it is 0, so JB will 0 and KB is don't care. Why? From 0 to 0 we already know that J should be in at 0 and KB is don't care, KB at don't care condition. Okay, and QC from 0 to 0. Similarly, J should be at 0 and K is K at don't care condition. Okay, so if we put one input here, what will happen? It will goes to 0 to up, it will count up and down. When we put 0, it will count from down to up. So from this table we see that present state is 0 0 and next state is 1 1 1. That means present state is 0, next state is 7. And here when present state is 7, what will happen? Next state is 6. From this binary code we already know that 110 is 6, so 7 to 6. Now here is present state now is 6 and our next state will be 5. So it count from down to up. Okay, from bottom to up. This is our all transition table. We fill up this in this technique. Let's see what happens in KMap. So from table we already know that there is 4 variable. Why? Because M is here exist. So M, Q, C, QB, QA. This is our 4 variable for present state. So this is our present state. Here we find what will happen. Here we fill up all KMap and we find this equation J. We already know how to fill this KMap, and we also find this K. Similarly, we find JB, KB, and also JC, KC. So from KMap we find this equation. Now this equation will be built in further. This will explain my fellow teammate Touhid alone. So thank you very much. This is all from my side. Assalamualaikum.
Assalamualaikum sir. Now I am going to discuss about how we build the diagram and the block diagram for our circuit and simulate the circuit. So in apparatus we can see, as we are building a 3-bit counter, we need 3 JK flip-flop. For that we can use the IC 7473 2 pieces, and we need 4 AND gates, 2 OR gates, 1 NOT gate, 1 digital clock for the pulse, 1 source voltage, and the DCD hex for displaying the numbers. So here is the block diagram for our required circuit. So in this block diagram I am going to explain what is happening. So when the up/down or our M is 1, the above line is working. So when it is working, the QA and the QB and the QC is doing forward counting, like from 0 to 1 to 3 4 5 7 and 0 again. But when the up/down bar counter is 0, the counter is going through this knot and its inputs is 1, so it is doing the backward counting by the Q bar. So and also here and it is counting backwards from 0 to 7 6 5 4 3 2 1 0. So here is the simulation setup for the circuit and the preset. Let me draw again. The preset and the reset is always 0, and we gave a clock pulse of 10 Hz, and this high is for the JA and KA, where the JA is K is 1, and the up/down button here, this button is the M, and it works if we need to do counting upwards or downwards. So let's see a short video of our simulation. Here you can see that our reset and preset key is 0, and when we start the simulation it starts counting upwards because our up/down bar count is sending signal 1, and when the signal is 0 it is doing counting backwards, and when it's 1 again it is again doing counting forward and backwards again, and so like that we can control the counting if we need upwards or downwards accordingly. So overall from this project we discussed about flip-flop and counters, also the mechanism of counters. We also learned about the asynchronous and synchronous counters. We also learned about sequential and non-sequential counters. And finally we designed a 3-bit bidirectional counter or up/down counter. And here are the references that we used for making this project. Thank you, sir.